In this video, we're going to go over an example of why functions are important in computer science. And these are the kinds of problems that you're going to run into in a computer science class for dealing with functions. So the first function we're going to talk about is an encoding and decoding functions. So it's really common to want to encode messages. So we know that digital messages are made up of a finite series of zeros and ones, right? That's just how all text or all messages are encoded in the computer. If we want to send a message from my computer to another computer, sometimes we modify these in such a way as to reduce interference. So one very simple modification could look like this. We'll have a rule, encoding rule, and this one's going to be replicate each digit 3 times. So what does that mean? So if I have a message 00101111 and I want to transmit this across a channel, from my computer to your computer via the internet, what I'm going to do is every time I see a digit, I'm going to create 3 of them. So here's a 1, so we get 3 ones, another 0. Okay, so here's an encoding of our digital message. Now, one reason this is done is imagine if during transmission there's some kind of interference. Possibly, what if somebody's trying to hack into our message, or maybe it's just noise in the channel, and this turns into a 1. Well, one of the advantages of an encoding scheme like this is I can look at this set of 3 and I can say, well, they're not all the same. So I know there's an error here. Even better, I can say with reasonable probability that 1 is the problem, because there should be 3 the same. If only one's different, it's probably going to be whatever the other 2 are. It's going to be a lot harder to randomly change 2 than it will be to change 1 out of this triple. So that's one reason this can be used, is this alerts the receiver to transmission problems. And in fact, this is exactly the kind of thing that's done when transmitting messages, though they usually use more sophisticated techniques than just tripling each digit. So this is an encoding function. We're not going to worry at the moment. We're not going to worry about having these errors enter the transmission. We're just going to think about the actual encoding and decoding schemes themselves. So here I'm going to name a set A, and I'm going to let A be the set of all strings of zeros and ones. So A is all binary digits. And then I'm going to have T be the set of all zeros and ones that are triples, right? That consist of consecutive triples of identical bits. So this is exactly the 2 sets we're talking about. We were talking about on the previous page. So I'm going to define this encoding function, E, which takes an element from set A and converts it to an element in set T as follows. Remember, A just consists of binary strings. So I'm going to take any binary string, little a in capital big A, and I'm going to say the encoding of A, or E of A, is the string obtained by replacing each bit of A by the same bit written 3 times. Okay, so again, if I have a 1, this is going to go 1, 1, 1. And if I have a 0, this is going to go 0, 0, 0. And then I'm going to define this decoding function. Decoding function D, and I'm going to define it similarly. I'm going to say that D of T, now notice T is a set of, in the triplets, so T is always going to have consecutive three zeros, then 3 ones, or, it's going to be sets of 3. And I'm going to decode that lowercase t and obtain the string obtained by replacing each consecutive triple of 3 identical bits, replacing by a single copy of that bit. So in other words, I'm going to be given 1, 1, 1. I'm going to convert it to a single 1. And given 0, 0, 0, I'm going to convert that to a single 0. All right, so we've got these two functions. We've got our encoding function, E, and our decoding function, D. So the question I want you to ask yourself is the encoding function E 1-to-1? Now remember, 1-to-1, a function is said to be 1-to-1 if no two elements of the domain match with the same element of the codomain. So can we ever have two different inputs get the same output with our encoding function? No, we can't, which means that this should be 1-to-1. So on this next slide, we're going to prove this. Okay, so I want to, here again is the definition of E. E of A is the string obtained by replacing each bit of A by the same bit written 3 times. And we're going to claim that this is 1-to-1. And let's prove this. And recall, this is how we do the proof. We say that this function f from x to y is 1-to-1 if and only if for all x1 and x2 and f, if f of x1 equals f of x2, then x1 equals x2. So let's just write that out. So proof. Suppose a1 and a2 are any binary strings such that E of A1 equals E of A2, right? That's this first part of our proof. So to do a direct proof, right, we start with the if clause, and I suppose it, and then we're going to try to show the then clause. So, since E replicates each bit, now you're going to notice that this is no longer numerical. In the previous examples, we did sort of algebra problems, but now we're using something more complex. We're using a function that's defined by a rule, and so now to do my proof, I need to talk about that rule. Since E replicates each bit 3 times, we can grab each set of 3 identical bits and replace it with a single bit of the same type to undo E. All right, so all E was defined to just take a bit and replicate it 3 times, right? We talked about E up here. And so I'm going to take each set of 3 and I'm going to replace it by 1. So I'm undoing E. And if I do this, to two identical strings, right, E of A1 and E of A2, we're going to get the same output. So therefore, E is 1 to 1. Now you'll notice, again, because this is no longer arithmetic, it's more conceptual. We're talking about this rule. We have a rule that replicates each bit of A by the same bit 3 times. And so we're going to say, well, if we have the output of this, so we have 2 identical triples right here, I'm going to undo that. I'm going to grab each set of 3 identical bits, and I'm going to replace it with a single bit to undo E, right? And if we started with the same 2 triplet strings here, the same 2 identical strings, then we're going to get the same output. And so again, a lot of times students struggle with this because there's not a formula. Instead, you really just want to describe what's going on. You have an algorithm based on a rule, so how would you deal with that? And this is an example. Let me make it a little cleaner. An example of how one would do that. Okay, so we showed that E was 1 to 1. How about onto? Is E onto? Well, remember that a function is onto if there's no element of the codomain that is not matched to an element of the domain. And in this case, the codomain is T. Right, so this is our codomain, and this is our domain. So if I take an element of the codomain, which is going to be sets of triples, right, am I always going to have a matching element in the domain? Am I going to always be, if I given this, can I always come up with an element in the domain A? Well, I'm going to argue that yes, we can. So E is onto, and on the next page we're going to prove that. Okay, so I'm going to claim that the encoding function E is onto. And recall how we prove that. We say it's onto if and only if for all y in our codomain there exists an element in our domain such that our function, given that element in the domain, gives us the y in our codomain. So first of all, I sort of gave a little example of that here. I drew this. I didn't really finish it, but we know that the element in our domain that matches this would be, I take 3 zeros and I give it, that's 1, 3 ones, 1, 3 ones, 1, 3 zeros, 0, 3 ones, 1. Okay, so given this element in our codomain, I can come up with an element in our domain that matches with it. Is that a proof? No, right? That's an example, and we cannot do universal proofs, right? This is definitely a universal conditional statement right here, a universal proof, a universal statement. So we cannot use an example to do it. Instead, again, we want to describe the situation, describe the algorithm, describe how, given an element from the codomain, we would figure out the matching element from the domain. So I'm going to let T be an element of T. And remember, big T is a set of triples. We want to show that there exists an element in our set A such that if I encode A, I get T, like that. So, since any element T of big T must, by definition, must contain consecutive triples of identical elements or identical bits, because remember that's how we define T. We said T was a set of all binary digits that have consecutive triples. Right? So that's the definition of T. So we know that any element in T will contain consecutive triples of identical bits. We can replace each triple with a single bit of the same type. And we'll call this new string A. Now, as always, we need to make sure that what we have derived, it belongs to the correct set. So, in a direct proof, when we come to a conclusion that we have 2 times A plus 1, we have to say, notice that A is an integer if we're talking about an odd number. Here, we need to show that little a is in the set of big A. Notice, is it in the set of big A? Yes, it is. A is in the set of big A because A is a set of all binary digits. A includes all binary strings right? By definition of E, if we give that stripped down string A, so remember we took T, which had consecutive triples, and we replace each triple with a single bit to get little a, which means if we then send little a to our encoding function E, it's going to give us back T, right? Since all this does undoes the work we did to get A. Right? So since we were able, no matter what set, what string, little t of big T, we were able to strip it, right? We were able to, here's an algorithm. There's an algorithm to replace digits with a single digits and get this string A. And then we found that if we hand that string A back to E, function E, we're going to get T. So this is exactly the definition of being onto, right? So therefore, E is onto. No matter what element of our codomain we get, we can find an element of our domain. And once again, we're doing all of this through an algorithmic description rather than a numerical description. So if we know that E is 1-to-1, right, which we proved, and that it's onto, then we know that it is a 1-to-1 correspondence. And if you were to go through, it's very similar to prove that D is a 1-to-1 correspondence. And in fact, E and D are inverses of each other, right? So a common feature of inverses is that they undo each other. So if I have an element of A, little a, and I encode it via E, I'm going to get an element of T. Let's call that A1 and T1. And similarly, actually, we don't need to do that. A and T. Similarly, if I take that same T, I can pass it through D and decode it and get A back. So this is a very common feature of inverses, is that they undo each other. All right, if you play around with algorithmic inverses, you'll find the same thing happens.